Hello, we are continuing to work on our prerequisite skills. In this next section, we're going to be solving some word problems involving formulas. Number 47, a rectangle has dimensions x by y. So a rectangle, we'll label one side x, one side y. The perimeter of the rectangle is 16, so the perimeter would be 2x plus 2y. We know that's equal to 16. Find the area of the rectangle as a function of x. Though the area of the rectangle is x times y, when it says find it as a function of x, it means find the area as a function of x. It means we should only have an a on the left-hand side of the equation, and on the right-hand equation, we should have an expression that only has an x in it. So somehow we need to eliminate the y from this area equation. And we're going to do that using a system of equations here. We're going to isolate the y in this first equation. So 2y equals 16 minus 2x. And then dividing both sides by 2, we have y equals 8 minus x. Now we can substitute this expression in for the y right here. Area equals x times 8 minus x. Area equals x times 8 minus x. And this is the area expressed as a function of x. Area is a function of x. Okay, next, find the area of an equilateral triangle with perimeter 18. So equilateral triangle, all three side lengths are the same. Perimeter is 18, so that means 6 and 6 and 6. And in an equilateral triangle, if we drop an altitude from one of the vertices, it's going to be a perpendicular bisector. So down here we have a 3 and a 3. And this is, of course, a right triangle. So we have a special right triangle. This is a 30, 60, 90 degree triangle. And the ratio of side lengths in a 30, 60, 90 degree triangle is 1 to square root of 3. 1 being the short leg, 2 being the hypotenuse, root 3 being the long leg. So short leg is 3, hypotenuse is double, and long leg is short leg times root 3. So 3 root 3. 3 root 3. I want the area of the equilateral triangle. So area is going to be 1/2 of the base times the height. 1/2, the base is 6. The height is 3 root 3. And then we just simplify. So 1/2 of 6 is 3 times 3 root 3 equals 9 root 3. 9 root 3. Two sides of an isosceles triangle are length x. So in an isosceles triangle, two sides are congruent. And they tell us two sides are x, so we have x and x. If the perimeter of the triangle is 50, find the area of the triangle as a function of x. Okay, so I don't know if we need to drop a bisector, a perpendicular bisector down here, but it might be helpful. We know the perimeter is 50, so I'm just going to call this side y. I don't know if it's equal to x. If it's x, it's an equilateral triangle, which is also isosceles, but it's not necessarily equal to x. So now this is y over 2. And we know that the perimeter of the triangle is 50. So 2x plus y equals 50. Now if I isolate the y, I have y equals 50 minus 2x. And I want to use this right triangle. So this is half of y. Half of y would be 25 minus x. Okay, so this is 25 minus x. Now I can use the Pythagorean theorem to get an expression for this third side in this right triangle. Pythagorean theorem tells us that the hypotenuse squared, so x is the hypotenuse squared equals leg squared plus the other leg squared. I guess I'll call that z for the moment. Okay, so hypotenuse squared equals leg squared plus leg squared. Let's see if that helps. And I've got, if I just take this x and this 25 minus x, that's going to be half of the perimeter. So x plus 25 minus x equals half. Oh, okay, that just worked me in a circle. That was not helpful. I think I'm going to have to use Pythagorean theorem here. Find the area of the triangle as a function of x. So the area of the triangle, 1/2 times the base times the height, is going to be 1/2 of the base times the height. 1/2 of the base is my 25 minus x. That's half of my base. Now the height is labeled as z right now, but I need to express that in terms of x. It has to be a function of x. So to get that, we're going to use Pythagorean theorem. Hypotenuse squared, I'm trying to get z, I guess, so I'll just take this equation and solve. Take the square root of both sides. The x squared minus 25 minus x squared equals z squared. If I take the square root of both sides, now technically I'm going to have plus or minus z, but since we're talking about the length of a side of a triangle, we can ignore the negative root, just use the positive root. So area equals 1/2 of the base, which is 25 minus x, times the height. The height is my expression for z, so square root x squared minus 25 minus x squared, like so. This is my area expressed in terms of x. Now, I could go a little bit further and simplify what's inside the square root, but the numbers are a little bit big and we're not using a calculator. So I'm going to just leave it like that. I'm going to leave it like that. All right, next. A cylindrical soup can has a volume of 2 inches cubed. So we've got a cylinder. Volume is 2. And the volume, let's see, we've got a radius and we've got a height here. So the volume would be the area of the base, pi times radius squared, times the height. That's going to be the volume. So pi r squared h is equal to 2. If the radius of the base is x, okay, so we're going to call the radius x. Instead of r, I can call it x. Find the surface area of the can, including the top and bottom, as a function of x. So pi, the radius is x, so pi x squared h equals 2. And I want the surface area. Surface area would be the area of the top, pi r squared, plus the area of the bottom, which is also pi r squared. So I'm just going to write 2 pi r squared, plus the lateral surface area around the side of the can. Lateral surface area would be the circumference of the circle, 2 pi r, times the height. And actually the r is an x here, so I'll make those r's x's. We're asked to express surface area in terms of x. This is a constant, this is a constant, this is in terms of x, constant in terms of x. Oh, this is the problem right here. We got to get rid of that h. So I'm going to come back up and use this as my helper equation. Isolate the h, or make h the subject of that equation, dividing both sides by pi x squared. H equals 2 over pi x squared. And now I simply need to substitute this in for my h. So surface area equals 2 pi x squared plus 2 pi x. Now I'm substituting in for h, 2 over pi x squared. And we can simplify. Pi divided by pi is just 1. X divided by x squared is going to be just x. 2 times 2 is 4. So surface area, 2 pi x squared plus 2 times 2 is 4 over x. This is surface area written as a function of x. Okay, a woman 5 feet tall stands x feet away from a 20-foot high lamppost. So lamppost, 20 feet. A woman, 5 feet tall. She's standing x feet away. Find the length of her shadow. So the light is shining down here, casting a shadow. So we'll say y is her shadow here. Find the length of the woman's shadow. So find y in terms of x. We want to write an expression for y in terms of x? Well, we have a right triangle inside of a right triangle. These are similar right triangles, so we can create a proportion. This short leg to this long leg would be equal to this short leg to this long leg. 5 over y, like that. There's our proportion. Now I'm going to make y the subject of this equation. So I'm going to cross multiply. 20 times y equals 5 times x plus y. I'm going to make y the subject of the equation. So let's distribute the 5. 5x plus 5y. Any term with a y on it, we move over to the left. 20y minus 5y is 15y equals 5x. I can divide by 5. 3y equals x. Actually, I'm trying to isolate the y, so y equals x over 3. Now y is written as a function of x. And y represents the length of her shadow. So there's our answer, x over 3. Find the distance from the origin to the point on the line y plus 2x equals negative 5 as a function of x. Okay, we don't need a graph, but it might help to understand what we're looking for. We've got this line. Let me write this line in slope-intercept form. So y equals negative 2x minus 5. All right, we've got this line, y-intercept of negative 5. Slope is negative 2. So this line is something like that. And we're trying to write an expression. If we just pick a generic point xy on the line, what is the distance from the origin to that point? Well, no matter where the point is on the line, we can make a perpendicular to the x-axis like so, creating a right triangle. This is x. This side here is y, xy. And so we can use Pythagorean theorem to get an expression for our hypotenuse, and the hypotenuse is the distance from the origin. The hypotenuse is the distance from the origin. So distance equals the square root of x squared plus y squared. And that's just distance formula or Pythagorean theorem. Okay, find the distance from the origin to the point on the line as a function of x. As a function of x means we don't want to see a y in our answer. We want distance. On the left-hand side, we have that already, d equals. On the right-hand side, we only want x as a variable. We don't want y, so we have to substitute something else in for y, and we have that right here. We know y is equal to negative 2x minus 5, so I'm going to make a substitution. So distance equals the square root of x squared plus, and that expression for y needs to get squared, negative 2x minus 5 squared. Okay, so I have it written as a function of x. The numbers are pretty small here, so we'll go ahead and take the extra step to simplify. X squared plus. Foiling that out, we get 4x squared minus 10x, and then plus 25. And we can combine the like terms here. We have 5x squared minus 20x plus 25. So this would be another way that we can express that answer, the distance as a function of x. In the next section, we're going to review inequalities and piecewise functions. So we're asked to solve. Remember, solve means find the value of x. Solve x squared minus 4x minus 12 greater than 0. This is an inequality. If it was an equation with an equal sign, we would want to factor the left-hand side. Right-hand side is 0, set each factor equal to 0. We're going to use that same strategy here, but that's not going to give us our final answer, but it'll give us a good start. So I can factor the left-hand side, two numbers that multiply to 12 and add to negative 4. It's going to be 6 and 2, negative 6 and positive 2. Negative 6 and positive 2. It's very easy to factor using this guess and check method when the leading coefficient is 1. Okay, then we have greater than 0. So x minus 6, x plus 2. What I'm going to do is make a number line. Now there's a couple of ways we can think about this. I can just stick with a number line only, just only a number line, and put my roots on the number line. So setting each one of these factors equal to 0 gives me a positive 6 and a negative 2. Those are the numbers I need to put on this number line. All right? It doesn't have to be drawn to scale, but just for reference, there's the 0 on the number line. Okay, so these are the points where it would be equal to 0. But we don't want to know where it's equal to 0. We want to know where it's greater than 0. So let me not make those closed circles. Let me make them open circles. They're not solutions. They would be where the expression is equal to 0. We want to know where it's greater than 0. Now, this expression right here, this is quadratic. And if I were to graph this quadratic, it would look like a parabola opening up. And I know it opens up because the leading coefficient is a positive number. It's positive 1. Right here, positive 1. So if I just, kind of roughly, okay, that's not a great sketch, but roughly sketch a parabola opening up, I can see from this sketch where this is going to be greater than 0. Where is it going to be greater than 0? Well, the number line itself represents where it's equal to 0. Where it's equal to 0. So greater than 0 means above 0. Positive. Where is it positive? Where are the y-coordinates positive? So I can see from my sketch here, whenever the x-coordinate is less than -2, or greater than 6. So that's my solution. X is less than -2 or x is greater than 6. It needs to be the word or, not the word and. The word or. X is less than -2 or x is greater than 6. Okay, let's try that again in the next example. It's already been factored for us. Solve x plus 2 times 1 minus x is less than 0. X plus 2 times 1 minus x is less than 0. If I set each one of these factors equal to 0, I'm going to get x equals -2 as a root and x equals 1 as a root. So I'm going to draw a number line, and I'm going to plot those two values on the number line. And we don't need to put the 0 there, but just for reference, it's there. This, if I were to multiply this back out, first times the leading term, actually the leading term would be the x times the -x. That's a -x squared. That is a parabola that opens down. Opens down. -x squared is the leading term if I were to simplify that expression on the left-hand side. Right-hand side is 0. That's important as well, but that's already been done for us. But just remember, we got to get one side equal to 0 before we use this strategy. So leading term, -x squared, has a negative coefficient. This is a parabola that opens down. I'm looking for less than, strictly less than, not where it's equal to 0, just less than. So again, open circle, open circle. But that's going to be kind of the boundary. Now this parabola opens down, opens down. So where is this parabola? Less than 0. Less than 0 is below 0. So that's going to be here and here. That's going to be where x is less than -2 or x is greater than 1. X is less than -2 or x is greater than 1. Next, solve 3x cubed minus 9x squared minus 30x less than or equal to 0. We're going to start by factoring. I see that all three terms on the left have a 3 in common. They also have an x in common, so let's factor out 3x. Factoring out a 3x means we're dividing each term by 3x, so that leaves me with an x squared minus 3x minus 10. And let me just distribute that back out to check and make sure I didn't make a mistake. 3x cubed minus 9x squared minus 30x. Looks good. Less than or equal to 0. This time it's or equal to 0. All right, let's see if we can factor the quadratic expression further. So 10, it could be 5 times 2 or 1 times 10. I'm trying to get 3 in the middle. So, and this is 1 times 1, so it's going to be 1 and 5 and then 1 and 2. 1 and 5 and then 1 and 2. Okay, 3x, x. I said 1 and 5 and then... Okay, so we need to get a -3. It's going to be like that. Let me FOIL that back out to check. X squared minus 5x plus 2x minus 10. Looks good. Getting the roots here. The roots, we have x equals 0, x equals -2, x equals 5. I get my roots by setting each factor equal to 0. Okay, and I'm going to go to the number line, and I'm going to plot those roots. So I have a -2, a 0, and a 5. This is cubic, it's not quadratic, so the graph doesn't look like a parabola. It does not look like a parabola. So I have to be a little bit careful here, but less than or equal to 0 means these are going to be solutions this time. So closed circles. This is where it's equal to 0. -2, 0, and 5. Those are the x values where this is equal to 0. But I also want to know where it's less than 0. So do we know what this graph looks like? It's cubic. It's cubic and it has 3 roots. Cubic and it has 3 roots. So it has to look like either this or it could be coming down like this. Okay, so we need to know which one it is. Let's think about the leading term. The leading term is 3x cubed. 3x cubed, it has a positive coefficient. So it's like this. This is a cubic with a positive leading coefficient. This is a cubic with a negative leading coefficient. Okay, so I don't know exactly what the graph looks like, but I know it's going to do this. It's going to do this. I want to know where this is less than or equal to 0. So now I can see, oh, here, less than, here, less than. And then we see where it's equal to 0 as well. So solutions, x less than or equal to -2, or now it's x between 0 and 5. X between 0 and 5. So 0 less than or equal to x less than or equal to 5, like that. Okay, now we've got a complex fraction, 2x minus x squared plus 1 over x, all over x, less than 0. Okay, this looks complicated. X squared plus 1 over x, less than 0. Now, thinking about the domain, I know that x equals 0 is not in the domain of this function. And the reason I know that is from this expression right here. You're not allowed to divide by 0, so x cannot equal 0. X cannot equal 0 in this problem. I know that's not part of the domain. X is not equal to 0. And since x is not equal to 0, I don't have to worry about any problems if I try and divide something by 0. So I'm going to just start by multiplying both sides by x. Oh, wait, actually I don't want to do that because it's an inequality. It's not an equation. It's an inequality. I don't want to do that. All right, let's just simplify the numerator instead. Let's simplify the numerator. I'm going to get a common denominator, so I'm going to multiply this by x over x. And that's going to give me 2x squared minus x squared plus 1. These are both now over x, so over x. And then that's all over x, less than 0. All right, dividing by x. Right here I'm dividing by x. And dividing by x is the same as multiplying by 1 over x, like that. So now numerator 2x minus x squared plus 1 times the 1 over x squared, like this, less than 0. Okay, then I'm going to distribute this negative. So 2x squared minus x squared minus 1 over x squared, less than 0. Combine like terms. This and this are like terms. Then I get x squared minus 1 over x squared, less than 0. Now, I don't know what the graph of this looks like, so I can't use exactly the same strategy I did in the quadratic example or the cubic example. X squared minus 1 over x squared equals 0. But I can factor x squared minus 1. And I can think about where would this equal 0? Where would this equal 0? Well, it's going to equal 0 when the numerator is 0. And to figure that out, we set each one of those factors equal to 0. So positive 1 and negative 1. Those x values, positive 1 and negative 1, are going to make this whole thing equal to 0. So positive 1 and negative 1. Make a number line, and I'm going to put that there. Now, I know that's where it's equal to 0, so that's not part of my solution. I'm going to put open circle. Now, I don't know exactly what this graph looks like, but all I really need to know is in each section, I've created 3 sections. We call these partitions, but I've created 3 partitions or 3 sections on this number line. And I need to know in each section whether the function is above the x-axis or the number line here, or below, above or below. So I'll just pick some test points. So let's say I want to check this section over here. So I'm going to let x equal -2. I'm just going to test it. -2 plus 1 times -2 minus 1 over -2 squared. That would be, in the numerator, negative 1 times negative 3 is positive. The numerator is positive. The denominator is positive. Positive divided by positive is positive. Let me erase this. Positive. So in that section, positive. Now let's pick a test point between negative 1 and 1. You might be tempted to pick 0. That's a nice number in the middle. However, we already said that doesn't work. 0 is not in the domain, so we're going to run into a problem if we try and substitute in a 0. That's not going to work. So instead I'm going to use, let's just use 0.9, 0.9, 0.9. 0.9 plus 1 is 1.9. 0.9 minus 1, that's a negative number. It's a negative number. And then in the denominator, 0.9 squared is positive. So I'm multiplying in the numerator a positive and a negative. That's going to give me a negative. I'm dividing by a positive, so this is negative right here. And then a number bigger than 1, I can try 2. That's going to be 3. 2 minus 1 is 1. And the bottom is positive, so that's going to be positive as well. So I'm looking to see where is this thing negative, where is it less than 0, and I can see it's in this section right here, this section right here. So my solution is going to be x between negative 1 and 1. We are not including the negative 1 and 1. Now I also have to be careful because remember we said 0 is not in the domain, so that's tricky here. We have to exclude the 0, so that's not quite right. So x is between negative 1 and 0, or x is between 0 and 1, like so. All right, next up we have absolute value. We're going to solve this absolute value inequality. We have the absolute value of 15x plus 8 less than or equal to 3. There's a few ways we can approach this. If we want to do it graphically, that's not a bad way to go, but without a calculator, you have to rely on your memory on how to graph these absolute value functions. What does the 15 do? What does that plus 8 do to the graph? And then try and figure out where it's less than or equal to 3. Another thing we can do is drop the absolute value. When we drop the absolute value, we do it by replacing the absolute value with plus or minus, like so. And then this represents now 2 separate equations. The positive one would just be 15x plus 8 is less than or equal to 3. The negative one, if we move the negative to the other side, so divide both sides by negative 1, we have 15x plus 8. When you divide by a negative number in an inequality, you have to reverse the direction of the symbol. Negative 3, like so. And then we just solve each of these equations separately. So 15x, we're going to subtract 8 on both sides, divide by 15, and that reduces to negative 1/3. Or, and then over here, subtract 8 on both sides, so negative 3 minus 8, and then divide by 15. Oh, didn't mean to do that. Divide by 15, equal to negative 11 over 15. So our solution, x is less than or equal to negative 1/3, or x is greater than or equal to negative 11 over 15. Okay, the other thing we have to be careful about is whether we need this to be an or an and, an or an and. The absolute value of x, it just looks like this. The 15x plus 8 is going to, the 15 is going to stretch this vertically, and the 8 is going to shift it. It's going to shift it to the left. So we want, this is going to be stretched and shifted, so I don't know, maybe it looks something more like this. We want to know where is it less than or equal to 3, less than or equal to 3. So it's actually going to be, since it's a less than or equal to, it's going to be an in-between. Now, which of these numbers is bigger, negative 1/3 or negative 11 over 15? So if we think about a number line, this is the same as negative 5 over 15, negative 5 over 15, negative 5 over 15. So negative 11 over 15 would be more out towards here. So we want x to be less than or equal to the negative 1/3, less than or equal to greater than or equal to the negative 11 over 15, greater than. So our solution is in between. So a better way to write this would be like this, negative 1/3. We can also keep it separate like I did up here, but I need to change it to an and. If I write it as two separate inequalities like that, I need to change that word in the middle to an and, because a solution is an x value where both of these statements are true at the same time. They're both true simultaneously. When we say or, then when we talk about the solution, it satisfies one or the other, but when we say and, it satisfies both. Okay, next one. Oh, next one is the only thing that's changing is the direction of the symbol. Let me see if I can bring that all back. Yep, symbol. So instead of being less than, we want greater than. So our solution is going to look like that. That's going to be, this was my negative 11 over 15 right here. This was my negative 5 over 15, or negative 1/3. So it's going to be x is less than or equal to negative 11 over 15, or this time it's an or. So on our number line, we're here or here this time. Here or here. Or x is greater than or equal to negative 1/3. Like so. Okay, next, make y the subject of the equation. So we need to isolate the y on one side of the equation. We have x equal to y squared minus 1. Y squared, if I add 1 to both sides, equals x plus 1. I need to isolate the y so I can take the square root of both sides. Now when I take the square root of y squared, the square root of y squared is not just equal to y. The square root of y squared is equal to plus or minus y. The square root of y squared equals plus or minus y. And actually this is a little bit lazy notation. It's actually a piecewise equation. The square root of y squared is equal to the absolute value of y. So is equal to either y or negative y, depending on whether y is positive or negative. If y is positive, it's just equal to y. If y is negative, then we have to make it equal to negative y. Okay, so just want to remember, whenever you take the square root of a variable squared, use plus or minus. Now we can move the plus or minus to the other side. Plus or minus means we're multiplying by plus or minus 1. So we can divide both sides by plus or minus 1, and it just puts the plus or minus on the other side. Plus or minus the square root of x plus 1. And now y is the subject of that equation. In the next section, we're going to be practicing some graphing. These is just very rough sketch. I just want you to know what the parent functions look like. You don't need a detailed graph with a scale and all of that. I just want to make sure that you have a general idea of what the shape is and where the key features are. So first one, y equals x. That is a linear function. Y equals x. Linear function. Slope of 1, it passes through the origin. Okay, y equals x. And it's got a point like 1, 1 if we want to establish a scale there. Okay, y equals x. Now, y equals x squared. That's a quadratic function. The graph looks like a parabola. Opening up. Here's the parent function. It also passes through the point 1, 1, y equals x squared, like so. Okay, the next one is y equals x cubed. Y equals x cubed. Parent function looks like this, and it also passes through the point 1, 1, y equals x cubed. Okay, so we need to have a general knowledge of the shape of the graph and any key important features like this. The vertex is an important feature. We know the vertex is at 0, 0 there. And this point where the concavity changes, point of inflection at 0, 0. This one passes through the origin as well, 0, 0. And slope of 1. Okay, next one, y equals square root of x. Y equals the square root of x. Looks like this. There's a point at the origin. 0, 0 also passes through 1, 1. y equals square root of x. It grows slowly. Y equals square root of x. Y equals cube root of x. The cube root of x is the inverse of x cubed. So x cubed looks like this. Its inverse is going to look like this. So cube root of x looks like this and this. 0, 0 also passes through 1, 1, and passes through negative 1, negative 1. Cube root of negative 1 is negative 1. Cube root of 1 is 1. Cube root of 0 is 0. Okay, then we have absolute value of x. The absolute value of x is a piecewise linear function. So it looks like y equals x on the right-hand side, and it looks like y equals negative x on the left-hand side. Y equals absolute value of x. Also passes through 1, 1. Vertex at 0, 0, and passes through negative 1, 1. Absolute value of x. Okay, next we have the parent exponential function y equals e to the x. Y equals e to the x. So we want to remember general shape y equals e to the x. This passes through the point 0, 1 because e to the power 0 is equal to 1. Y equals e to the x, e to the x. And then 1 over x. 1 over x is called the reciprocal function. Now this graph, it has some asymptotes. It has a vertical asymptote on the y-axis. It has a horizontal asymptote on the x-axis. So it does not pass through the origin. And it has the shape of a hyperbola. A hyperbola. It looks like that. It passes through the point 1, 1. So 1 over 1 is 1. And then also passes through the point negative 1, negative 1. So 1 over negative 1 equals negative 1. Those are our parent functions. We will be working with all of those parent functions in this course, so it's important to know what they look like. Next, we're going to transform some of these parent functions. Sketch the graph for y equals negative x plus 3 squared. So we can start with the parent function. The parent function for this is y equals x squared. Y equals x squared. So we know that's a parabola opening up, vertex at the origin. Now the plus 3 is going to shift this left 3 units. Left 3. So left 3, you know, it would look like that. But we have this negative here as well, and that is going to affect the graph by reflecting it across the x-axis. So this is going to open now down, left 3, and it opens down. If we want a more detailed sketch, then we can find some intercepts and get a little bit better graph. But for now, I just want you to have just a rough idea of what these graphs look like. Okay, the next one, g of x. Here, the parent function is just y equals square root of x. So here's that parent function, y equals square root of x. And we have some transformations. Minus 2, she's going to shift it to the right 2. Right 2. Right 2. And then this minus 1 is going to shift it down 1. So it's going to look like that. Okay. The next one, parent function, would be y equals absolute value of x. Y equals absolute value of x. So that piecewise linear function. And then we have some transformations here. Plus 3 is going to make it go left 3. 1, 2, 3. And the plus 5 is going to make it go up 5. 1, 2, 3, 4, 5. Left 3, up 5. And then it's going to have a slope of 1 on the right and negative 1 on the left. So it will look like that. And then the next one is a parent function is cubic. Y equals x cubed. And we have a couple transformations. Plus 2 is going to shift it up 2. This negative is going to reflect it across the x-axis. Okay, so reflect across. Normally, y equals x cubed looks like this. But it's going to be reflected across the x-axis. So that's going to make it look like this. But then it's also being shifted up 2. Up 2. Go up 2. So we're going down on the right, we're going up on the left, like that. It should look symmetric. My sketch is a little bit off. Okay, if you are having some trouble with sketching these, I didn't show this, but you can always plot points. Make yourself a little XY table and just plot some points. Try, okay, when x is 0, maybe when x is -1, 1, 2, -2. Those would be some good points that you can substitute into the equation, and then plot the points, and hopefully you'll be able to know the general shape of the graph so you can get a good sketch from there. Okay, 65, we need to be a little more detailed here because we're asked to identify x-intercepts, y-intercepts, and asymptotes. These are called rational functions, To find the x-intercept, we let y equal 0. To find a y-intercept, we let x equal 0, so that's usually easier. And then to find asymptotes, well, let me wait and explain that here in a minute. So first of all, our x-intercepts, we let y equal 0. This is a fraction. A fraction is only equal to 0 when the numerator is equal to 0. So I'm finding x-intercept right now. All right, so I set the numerator equal to 0. We practiced solving these quadratics already. This is factorable. X plus 1, x plus 2 equals 0. So set each factor equal to 0. X equals -1 or -2. That means I have 2 x-intercepts. So x-intercepts. Don't just write down a number. You can write x equals -1, x equals -2, or write the points. The x-intercept is where y is 0. So -1, 0, -2, 0, like that. To get a y-intercept, you're going to let x equal 0. So x-intercept, let y equal 0. Y-intercept, let x equal 0. That's easy. So y equals, x is 0, 0 plus 0 plus 2, over 0 minus 4. That's -1/2. So y-intercept is when x equals 0. Okay, there's my y-intercept. Now, asymptotes. For horizontal asymptote, I am going to compare the leading term in the numerator and the denominator. And I'm just going to look at that ratio. If they have the same degree, I'm going to simplify. X squared over 4x squared reduces to 1 over 4. I'm just looking at the ratio of these coefficients. There's a 1 in front of that x squared, right? So 1/4. Y equals 1/4. That is a horizontal asymptote. Y equals 1/4. When they have the same degree, we look at the ratio of the coefficients. For vertical asymptote, I'm going to let the denominator equal 0. 4x squared minus 4 equals 0. Dividing by 0 can help us find, like dividing by 0 can be where we have a vertical asymptote. That's not always true though. So we can't just set the denominator equal to 0 and solve. We have to make sure that whatever solution we get does not also make the numerator 0. All right, but let's solve this. We can factor out a 4, and then that factors again, x plus 1, x minus 1. So we have 2 solutions here, x equals -1 or 1. Now, do either one of those solutions make the numerator 0? The numerator 0. Yes, I believe so, because we had right here, when we set the numerator equal to 0 and solved, we got -1. So if I go back now and I check when x is -1, what happens in the numerator? We get 1 minus 3 plus 2, that's 0. And if x is -1, I get 4 minus 4, that's 0. So when you get 0 over 0, 0 over 0, that's not a vertical asymptote. That is a hole in the graph. We call that a removable discontinuity. That is a hole in the graph. So actually, it's not an x-intercept. I need to cross that off my list. It's not an x-intercept. That is a hole in the graph. Okay. So vertical asymptote only at x equals 1. Horizontal asymptote y equals 1/4. There is a hole in the graph at x equals -1. There is an x-intercept at -2, 0, and there is a y-intercept at 0, -1/2. Okay, so that was a lot of information for that graph. Next, we have y equals x over x squared minus 3x minus 4. So x-intercept, we're going to let y equal 0. 0 equals x over x squared minus 3x minus 4. This is a fraction. Fraction will only equal 0 when the numerator is 0. So we just get x equals 0. For an x-intercept, that's 0, 0, 0. 0, 0. 0, 0. I'll check for holes in the graph, so we may have to throw that out, but for now I'm going to say 0, 0. Y-intercept, I'll let x equal 0. If I let x equal 0, I get y equals 0 over 0 minus 0 minus 4. 0 divided by negative 4. 0 divided by negative 4 equals 0. So y equals 0 is the y-intercept, and that's coordinates 0, 0. That's the origin, right? So we already found that origin. Asymptotes. Okay, when I look at my leading terms, x, x squared, they don't have the same degree. They don't have the same degree. If they had the same degree, I would just divide and look at the ratio of the leading coefficients, but they don't have the same degree. The denominator has a larger degree. So this denominator in this fraction is growing faster than the numerator for large values of x. When x is getting infinitely large, the denominator is much, 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 much bigger than the numerator. And that means this is approaching y equals 0. So I have a horizontal asymptote at y equals 0. All right, now this is interesting because I said I had an intercept at y equals 0. How can we have an asymptote and an intercept at the same point? Let's think about that. We'll come back to that. Okay, and then for vertical asymptote, I set the denominator equals 0. Vertical asymptote, let the denominator equal 0. X minus 4 equals 0. Solve, we get x equals 4. Does x equal 4 make the numerator 0? No, because when I set the numerator equal to 0, oh, I'm looking at the wrong equation. Wait, that's not, here's my denominator right here, sorry. Okay, x squared minus 3x minus 4. Set that equal to 0. Okay, is it factorable? Multiply to 4, add to negative 3. Does that work? X squared minus 4x plus x minus 4. Yes, good. So we get x equals negative 1, positive 4. Do either of those values make the numerator 0? No, because when I set the numerator equal to 0 and solved, I only got x equals 0 as a solution. Okay, so two vertical asymptotes. Vertical asymptote at x equals negative 1, x equals 4. Okay. So this is a common misconception that people think that a graph, if it has an asymptote, a horizontal asymptote at y equals 0, for example, that there are no points on the line y equals 0. But that's actually not true. That's not true. The graph can pass through a horizontal asymptote. It is possible. It just won't happen at the end. It won't happen in the end behavior of the graph, but it can happen in the interior of the graph. All right, so we have x and y intercepts at the origin. We have a horizontal asymptote at y equals 0, and then we have two vertical asymptotes. So this graph is actually quite complex. We have an intercept at the origin. We have vertical asymptote here, x equals negative 1. We have a vertical asymptote here, x equals 4. We have a horizontal asymptote here at y equals 0. And then to know what that graph actually looks like, I might need to plot a couple of points. So let's come back and look at this equation right here. I'm just going to plot a couple of points in each section. So at negative 2, at x equals negative 2, I've got negative 2 over 4 plus 6 minus 4, negative 1/3. So negative 2, negative 1/3. Okay, that tells me this part of the graph looks like that. Then let's see what happens at x equals 1. At x equals 1, I've got 1 over 1 minus 3 minus 4. That's 1 over negative 6. 1 over negative 6. The graph is like here. Okay, then I also, so I know it's going to be going down like this, but I don't know if it turns like that or, so I didn't mean to make that so wobbly, or if it goes like that. Right, there's two possibilities there, so I kind of need to, this is a little bit annoying. I have to substitute in negative 1/2 to understand what's going on. Negative 1/2. And you don't have to do this. I'm just doing extra work right now. I don't know why I'm doing this. Numerator, negative 1/2. Denominator, negative 1/2 squared is 1/4. Minus 3, so that's going to be positive 3 over 2, and then minus 4. I just want to see if this is positive or negative. So 1/4 and 6 7/4. 7/4 minus 16/4, negative, negative, positive. Oh, so I think it does this. I'm kind of going in a hurry, so hopefully I didn't make a mistake. I think it does that. And then when x is 5, oh boy, 5 over 25 minus 15 minus 4, that's positive. So the graph is up here like that. Pretty sure that's what that graph looks like. Okay, and then the last one here, we want intercepts and asymptotes. So x-intercept, let y equal 0. 0 equals 2x squared minus 6x minus 8. I'm just going to let the numerator equal to 0. Fraction can only equal 0 when the numerator is 0. I can factor out a 2. X squared minus 3x minus 4. Is that factorable? 4 and 1 minus plus x squared minus 3x minus 4. Yeah, looks good. So we get x equals negative 1, x equals 4. So x-intercepts, negative 1, 0, 4, 0. Okay, y-intercept, we let x equal 0. So we get negative 8 over negative 4 equals a positive 2. So 2, 0 for the y-intercept. Asymptotes, now looking at the leading terms, the degree in the numerator is larger. That means no horizontal asymptote. No horizontal asymptote. The graph is just going to go off to infinity or negative infinity at the end behavior. And then for vertical asymptote, we want to let the denominator equal 0. Vertical asymptote, let the denominator equal 0. Oh, x minus 4 equals 0. We get x equals 4. Now that is a repeat solution from up here. 4, that means 4's, when I substitute in 4, I'm going to get 0 over 0. It is not an asymptote. Not an asymptote. That's a hole. That's a hole in the graph. Hole in the graph at x equals 4. Okay. We're almost done. Almost done. This last section here, exponents, exponential functions, logarithmic functions. Simplify. Simplify. So I can factor out an x in the numerator. X minus 1, and then x to the power 1/2. I'm going to subtract exponents. That's x to the power 1, x to the power 1/2. I'm going to subtract exponents because I'm dividing terms with the same base. So that's going to be 1 minus 1/2 is 1/2, and then x minus 1. I can also write that as square root of x times x minus 1. Okay, simplify. So I want to factor out what they have in common. I see x to the 1/2. I see x to the negative 1/2. I'm going to take the smaller of the exponents, x to the negative 1/2, and factor that out. Factoring out means dividing. So I have to take this term right here and divide it by x to the power negative 1/2. X to the power negative 1/2. So I'm subtracting an exponent. 1/2 minus negative 1/2. 1/2 minus negative 1/2 is 1/2 plus 1/2 is 1. So it's x to the power 1 times 8x cubed. Okay, this is getting complicated. Then I'm factoring out x to the negative 1/2. That just comes out x to the 4th plus 3 over x. Then I can simplify this right here. Subtract the exponents. There's a 1 right here. Negative 1/2 minus 1. That's x to the negative 3/2. And then here, distribute, or not distribute, just multiply. So I have 8x to the 4th minus x to the 4th minus 3. And then all this, oh no, not over x, because we got rid of that already. But x to the negative 3/2, that can move into the denominator. X to the negative 3/2 becomes x to the positive 3/2 in the denominator. In the numerator, we have 7x to the 4th minus 3. 7x to the 4th minus 3. Okay, now simplifying, it doesn't specify what form the final answer should be in, so let's just simplify so that we don't have negative exponents. There is more I could do. I can split this into 2 fractions and continue to simplify, but I think it's fine to leave it like that. All right, next one. We can factor out from this expression, we can factor out an e to the x. I can factor out an e to the x. Factoring out means dividing, so 2e to the x divided by e to the x leaves a 2. E to the 2x divided by e to the x, subtract the exponents, you have e to the x, like so. Here, when you're multiplying numbers with the same base, you add the exponents, and negative x plus x is 0. So we get e to the power 0 times 2 plus e to the power x. E to the power 0 is 1. So this is just 2 plus e to the x. 2 plus e to the x. If f equals e to the x minus 3x, then f of ln 2. So I'm going to highlight the input. The rule for this function is e to the power input minus 3 times input. And our new input is ln 2. So everywhere I highlighted an x, we're replacing it with ln 2. F of, replace the x with ln 2. E to the x, replace the x with ln 2. 3 times x, replace the x with ln 2. E to the ln 2, there's a rule for simplifying exponentials and log composition. That's just equal to 2. E to the ln 2 is just equal to 2. Minus 3 ln 2. Now we can leave the answer like this. We can also use a property of logs that allows us to move the 3 into the exponent. So I could write my answer like ln of 2 to the power 3. 2 to the power 3 is 8. So I could write my answer like this as well. Okay, make y the subject of the equation. ln y equals x plus 2. I'm going to exponentiate both sides. E to the ln y equals e to the x plus 2, like so. Then use my property of logs to simplify. That's just a y on the left, e to the x plus 2, like so. If 100 equals 24e to the power 5k, find the exact value of k. The exact value of k. So I can start by dividing both sides by 24. Then take the natural log of both sides. The natural log of 100 over 24, I guess I could reduce 100 over 24. It's 50 over 12, or 25 over 6. 25 over 6. 25 over 6 equals the natural log of e to the power 5k. So we have this property of logs as well. That's going to cancel out and say ln of 25 over 6 equals 5 times k. I'm solving for k, so I divide both sides by 5. Dividing both sides by 5 is the same as multiplying by 1/5. 1/5 ln 25 over 6 equals k. All right, then our last problem. Simplify. ln x plus 1 minus 2 ln x minus 1. I need to use some properties of logs here. The first thing I'm going to do is move this 2 into the exponent position there. So ln x plus 1 minus ln x minus 1 squared, like so. When we subtract 2 logs, we can condense them by dividing. We make a quotient x plus 1 over x minus 1 squared. So we've condensed this into a single logarithm. All right, I think we made it to the end. We did a lot of review, but these are all really good algebra skills, geometry skills that are going to help us be successful this year in this course.